Okay. All right, chapter 4. Chapter 4 is a magnetic field. Okay, magnetic field is a brand new, I would say is a brand new subtopic, brand new category in your syllabus. Okay, so previously we have been focusing on electric field, electric force, electric currents. They are all about electric charge. So when it comes to chapter 4 and chapter 5, we are going to focus on magnetic field, magnetic inductions, and so on. Okay, we're going to look at what happens from a magnetic field. Now, chapter 4, it is your assignments topic. Okay, now by right, when it comes out as an assignment, it shouldn't come out in the exams, right? But chapter 4, you still have to know how to solve the questions. Why? Because you need to apply the concept in chapter 5. Okay, they are related. So even though chapter 4 will come out in your will come out as an assignment, but you still need to know how to use all these equations, how it works in order to understand the concept in chapter 5. So don't just assume after you finish the assignment, then straight away you can forget about this topic. No, all right, because you need it for chapter 5. So define electric field. Electric field is a region. So when it comes to field, it refers to a regions. Okay, so electric field is a regions around the charge. So a magnetic field is a regions around magnet, where a magnetic force can be experienced. So if you put a magnet bar here, they can feel attractive force or repulsive force. Then they are there's a magnetic force in between them. Okay, that is the magnetic field region. But if you put another magnet at here and it oops. Okay, if you put another piece of magnet at this position and it doesn't feel anything, there's no magnetic force being exerted on it, then we say it is not being located inside the regions of the magnetic field. All right, so the idea is very similar to what we have learned in chapter 1. Okay, the electric field. In terms of the line, how you draw it, and so on, okay, they are quite similar. We'll go through it in a bit. So a stationary electric charge is surrounded by electric field. That is what we know, right? And when this charge is start to move, okay, then it begins to have magnetic field. Okay, it is surrounded by both electric field and magnetic field. So you look at this two statement, it's very important. If it is not moving, then you have only electric field. But if it is moving, then it has both electric field and magnetic field. If you are looking at charge, okay, of course, if you're looking at magnetic bar, then it has just a magnetic field. But if you're looking at what happens to a charge itself, it has electric field. When it's moving, it has both electric and magnetic field. Now, one more thing that you have to know. When it is moving and it is moving inside another magnetic field, then it will have magnetic force. And that is the things that we're going to go through as well today. All right. So electron that is not moving, it has electric field. Okay, electric field. And then if it is moving, then it has both electric and magnetic field. If it is moving inside another field, okay, this is your magnetic field. Okay, this is your magnetic field. If it is moving inside another magnetic field, then it experiences magnetic force. So that is the basic idea. How to distinguish between these three terms? So magnetic field has two poles. Okay, so when it comes to electric, we have positive charge and negative charge. When it comes to magnetic field, we're not looking at the sign of the charge first. We're looking at the pole. Okay, pole is the things that we use to draw the field, to sketch the field. So we have a north pole and we have a south pole. And this pole, they always come in pairs. What does it mean? You won't have a magnet with just one pole. That is impossible. Okay, so even if you have a magnet, for example, the first one, S pole on the left-hand side, north pole on the right-hand side, when you break it apart, okay, then it will just become south, north. It always comes in pairs. If you break it furthermore, then every single pieces, it comes with its own south pole and north pole, right? And then like pole repel each other, opposite pole attract each other. So if you put two magnets with the same pole, for example, north and north, then they will repel. Okay, if you put south and south, they will repel as well. But if you put a north pole and a south pole together, they will have an attractive force in between them. So the idea again is very similar to the charge. When it comes to chapter 1, remember, we have same charge or like charge, positive, positive, they repel. And then negative, negative, they repel. Positive, negative, attract. All right. So, okay, that is a bit of characteristic about magnetic field. So now let us see how to sketch it. Okay, how to sketch an magnetic field. So first of all, okay, wait, where's my arrow? All right. First of all, let us go through the learning outcome first. So learning outcome, identify magnetic field source. Sketch magnetic field line for, okay, you need to know how to sketch magnetic field line for magnetic bars. It's very simple. Current, also quite simple. If you know how to determine how to draw it. And the one that I wanted to take note is the Earth magnetic field. The Earth magnetic field, it is a bit special. Okay, we'll go through it after a bit. So now let us go through the magnetic field line first. Sketch magnetic field line. Okay, identify magnetic field source. The source, we can have it from the charge. Okay, from the this tree also. Magnetic bar will give us a magnetic field. Current carrying conductor with a moving charge will give us magnetic field. Earth magnetic field, Earth itself will give us magnetic field as well. So these are the three sources. Okay, the three sources that can generate, that can give us magnetic field. So now let us go through how to sketch magnetic field line. Okay, how to sketch magnetic field line for every single case, for every single source. So first, magnetic field line, they are used to represent magnetic field. So magnetic field, just now we are talking about regions where object can experience magnetic force. So how do we know the regions covers until which positions, covered until where the surface area that's being covered by the magnetic field, the region? We use magnetic field line. Okay, we use magnetic field lines to represent the region. And by conventions, magnetic field lines, it leaves North Pole and it enters South Pole. Okay, it leaves North Pole and enters South Pole. That is the things that you must memorize. A magnetic field line can be represented by a straight line or curve. The tangent to the curved line, it indicates the directions of the magnetic field. What does it mean by tangent once again? So for example, now you have a magnetic bar. Okay, so this is the North Pole, this is the South Pole. So it's leaving North Pole, it's entering South Pole. If you have a straight line, it's very simple. Straight away, it represents the direction. Okay, it represents direction. But sometimes, okay, sometimes you won't have a straight line. Okay, you will have a curved line like this. Okay, curved line leaving, curved line entering. So how are we going to determine the directions at a certain position? Again, okay, let's say you want to determine the direction at this position. You draw a straight line that is only touching it at this point itself, and it is always perpendicular to this point. Okay, this curve. So, okay, so let's assume this is the radius of the curve. So it is perpendicular to the radius. So this is what we call tangent line. And this tangent line, it represents the direction at this point, okay, at this particular point. So you need to understand what does it mean by tangent and how to determine the directions when you have a curved line, especially when it comes to current carrying conductor. Okay, current carrying conductor, if you have current flowing up, this is the directions of magnetic field. So how are you going to determine the directions of magnetic field at a certain position? For example, here, then let's say this is the radius, then it is always perpendicular to the radius. And this represents a direction at this particular point, at this one point. All right, so tangent, okay, tangent, it is a perpendicular to the radius of the curve. And then the directions, the line, tangent line, we use it to represent the directions of magnetic field at that one point. So magnetic field can be represented by crosses or dotted line as shown in figure. Now, if it is not pointing to the right or to the left-hand side, going up or going down in a 2D surface, but if it is going into or out of the page, then we use a cross or the dotted point to represent the direction, okay, to represent the direction. So if you are using a cross, okay, a cross or an X, then it represents enter, going into the page. Another term that we always use in our questions is into the page. Okay, is into the page. And then if you have a dot, okay, you are drawing a black color dot, then this is leave the page, or we say out of the page. Okay, write it down. Yeah, these two statements, they are often being used in a question, and that is how we describe the direction in your final answer: into the page or out of the page, to the left, to the right, upward, downward. All right. So another way that I can help you, okay, to remember this cross or dot is you try to imagine. Now you have an arrow, okay, you have an arrow. You are trying to hunt with an arrow. So kalau kamu memanah, okay, memanah. So if you shoot this arrow into the page, you shoot it to the wall in front of you. What you are seeing from the back is a cross. Okay, you're looking at a cross, you observe a cross at the back. What are you going to see if the arrow is being shot at you? Okay, you will see the end of your life, all right, if it is being shot at you. So if you look at it from the front, you are going to see a dot. Okay, you will see just a dot that is coming from the head of the arrow. So kalau kamu observe memanah ini, okay, dari belakang, kamu akan nampak pangkat dari belakang. Okay, so because it is moving away from you, it is being shot into the wall. And if we say out of the page, basically it's pointing towards you. So now the arrow, okay, memanah ini, dia anak panah ini dia menghala ke Anda. Okay, when it is pointing towards you, what you observe from the front is just a dot. Okay, the arrow and then the metals around the nips. You will see a circle when it's pointing towards you. So out of the page, basically it means it is coming towards you. Into the page means it is away from you. Okay, in another words. So that is what you are going to observe. All right, so let's see what is next. Okay, what's next? So next we have, okay, the line. So a uniform field line. Okay, just now we look at what happened if it's into or out of the page. But now if you're observing it from the side, so a uniform field line is represented by a parallel lines of force. This means that the numbers of lines passing through the perpendicular through an area, unit area, at all cross-sectional. Let me repeat it again. This means that the numbers of lines passing perpendicularly through unit area at all cross-section, meaning that is your cross-sectional area at all points. In the magnetic field, they are the same. All right. So now if you put a circle, a ring right here, kalau kamu letak ring di sini, and another ring at here, the numbers of line passes through it, they are equal. That is what we call uniform. But if you have a non-uniform field lines, then it is being represented by a non-parallel line. Okay, just now we have uniform, and now we have non-uniform. If you have a non-uniform magnetic field, okay, now you put a ring right here. What are you going to observe is that the numbers of line passes through it has now decreased. Okay, when the line is spread out. Kalau line spread out seperti yang ditunjuk dalam gambar raja, means that now you have less line passes through this ring. Okay, passes through this cross-sectional area. So if less line passes through it, what does it mean? It means that now you have a weaker field strength. Okay, if you have less line passes through it, now it is a weaker field in the cross-sectional area A2. But if you have a more line passes through it, then you have a stronger magnetic field strength at this position, at the positions at A1. Okay, so same as electric field, numbers of lines represents the strength of the field. More lines passes through the same cross-sectional area means that the field strength is stronger. If you have lesser line passes through the same cross-sectional area, same surface area, then it means you have a weaker field. Okay, weaker field strength. So that is a characteristic, and that is the things that you have to take note if the question asks you to sketch magnetic field line. Okay, if the questions ask you to sketch a magnetic field line, for example, you are given two magnetic bar. Okay, you're given two magnetic bar. Now it tells you this one it has a higher field strength. This one has a lower field strength. Then the numbers of line, they must be unequal. Okay, but if both of them, you're using the same type of a magnet, they have the same strength, then the numbers of line must be equal. Okay, dia sama. Idea dia exactly sama macam kita punya electric field. Okay, dari segi bilangan line, dari segi dia punya strength dan sebagainya. So how are we going to sketch magnetic field lines pattern? There are a few patterns that you need to know because it might come out in the exam. First, if you have one magnetic bar itself, it also comes with magnetic field line. Why? Because every magnetic bar, it comes with north pole and south pole. Okay, north and south pole. So the line is leaving north pole and it's entering south pole. Okay, it's leaving north and it's going towards the south. And at the end, you just put one is leaving like this, and then all the lines coming out, and the other end, the south pole, you must show that there's a magnetic field line entering the south pole. All right. If you have a horseshoes or the U-shaped magnet, that is how it looks like. Also from north to south, but as it gets further away, as you can see, the distance increase. Okay, because it becomes less strong. Okay, the strength decrease as it gets further away from the source, from the pole. Okay, the ones that I want you to take notes is the diagram right here. Two magnetic bars like pole and two magnetic bar unlike pole. Okay, there's a typing error here. Unlike pole. Like poles and unlike pole. Like poles is very simple. You look at the sign, okay, you look at the pole. If you have north pole, then all lines they are leaving. But one thing I want you to add in the diagram, when you have a north pole like this, at the middle, at the center right here, there is a neutral point. Okay, there's a neutral point. It means that totally no field at this position. Okay, no field at this position. And again, same as your electric field, they won't cross each other. They won't overlap with each other. So remember, no overlapping. Okay, no overlapping when you try to solve the questions, when you sketch the diagram. So numbers of line represents the strength, and then the arrow also represents the direction, meaning that this is also a vector. All right, your magnetic field is also a vector quantity because it has a direction and it has a strength. And then at the center right here, total magnetic field, okay, the force, they are being cancelled out. So at this point, we call it neutral point. Okay, di titik tengah-tengah di sini. So you take you put it in your diagram, okay? Because if I'm not mistaken, you need to state neutral point in your exam. Without neutral point, 1 mark will be deducted. If I remember correctly. Okay, kamu mesti tunjuk titik ini. So if you have two magnetic bar with unlike pole, okay, the field line is leaving north pole and is entering south pole. All right, and at the same time, now this is what happened. Okay, this is what happened. This is a north pole. This is a south pole. This is north. This is south. According to the diagram given right here, okay, we have a field line. Okay, we have a field line like this. Okay, field line like this. Wait, yeah. Oops, I labeled the wrong pole right here. Okay, so this is a diagram given. Okay, as an okay, and then I have here. Now, other than the lines given in the diagram, what happened is that the field line is also leaving from north pole towards its own south pole. Okay, this is what happened in reality. Okay, this is what happened in reality. Dia keluar juga daripada north pole sendiri dan kembali balik ke south pole sendiri. So both magnet, they have their own magnetic field as well. So this is a complete diagram. Okay, so you have a entering, leaving. So this is a complete diagram when it comes to two pieces of magnetic bar. All right, so I would prefer you to remember this one, okay, because this is a complete diagram. It shows you what happened between two pieces of magnet and also what happens inside itself, okay, and also what happens inside itself. Of course, when it comes to a magnetic bar with like pole, same things happen, okay, same things happen. You have a field leaving north pole, entering south pole, leaving north pole, entering south pole. On both sides, okay, upper side and a downward side. So both sides, you have a magnetic field. It's coming in all directions, basically, right? So I give you 2 minutes, okay, for 2 minutes for you to record all this additional thing, for you to write down a bit of a notes for yourself, such as what happens in a U-shaped magnet, what happens when you have 2 light pole, and don't forget to make a corrections like here, okay, here, you have 2 unlike pole, okay, you have 2 unlike pole. So not like poles, but unlike poles. So what happens when you have unlike poles? So you can just add it in your own diagram. Okay, you can just add it. But then it becomes not very nice looking lah, of course. Right, so I give it some time to make a correction. And then we will see what happens on our Earth. Okay, we'll look at Earth magnetic field. Okay, so now let us go through the Earth magnetic field. Oops. Okay, Earth magnetic field. So Earth magnetic field, note that the Earth North Pole is acting as, don't get confused. We have 2 different poles at every position. Okay, Earth North Pole is acting as a south magnetic pole. Okay, whereas when you look at the Earth South Pole, okay, geographical South Pole, it is acting as a north magnetic pole. So what does it mean? Okay, if you look at the map, kalau kamu tengok peta, okay, kutub selatan, okay, your south, kutub selatan south kan, yes, your south geographic pole, okay, geographical south pole, your Earth South Pole, dalam peta dia tunjuk kutub selatan, that one is actually acting as your north magnetic pole. Okay, dia sebenarnya adalah kutub utara dalam kita punya magnet. So you try to imagine the Earth as a piece of magnet. Okay, so south geographic pole, geographical south pole is acting as a north magnetic pole, whereas geographical north pole is acting as a south magnetic pole. Why? Kenapa? Kenapa kita panggil sini kutub utara? Okay, dalam peta kita, kenapa kita panggil dia kutub utara? Kenapa kita panggil dia kutub selatan? That is because if you take a piece of a compass, okay, if you take a compass always pointing towards the south pole, right, towards the north pole, okay? So when they create a compass, they look at this compass, it shows that north pole, it points towards north pole. It shows that here is the north pole, okay? The line, okay, it shows that here is a north pole. That's why they call it a north pole, the Earth North Pole, geographical North Pole. But how do I know this is acting as a south magnetic pole? Because what we do know is that magnetic field is leaving North Pole and is entering South Pole. If you're holding a compass at this position, okay, kalau kamu pegang compass di sini, okay, the line passes through our compass. It shows that now my line is moving upward. But now you're standing on the surface of the Earth, right? So the line of the compass is moving upwards, but then what we do know is the line is leaving the compass and then is entering the Earth. That's why we know, even though in our map, okay, geographically we call it North Pole because our compass, it shows that that one is North Pole, but when it comes to a magnet, when you treat it as a peak of magnet, the reason why this North Pole is being attracted upward, that is because the Earth is acting as a South Pole. Okay, so ya, ada soalan? Kevin? Ada? Tertekan? Okay, tak ada masalah. Okay, so the reasons, okay, sebab kenapa kita tahu dia acting sini adalah South Pole, sebab kalau kamu bayangkan kamu yang berdiri di atas Earth, okay, you're holding the magnet, you're holding the compass. Compass dia tunjuk ke atas. North Pole dia menunjukkan North Pole compass kita tertarik ke atas. Tertarik ke atas, why? Because it has an unlike pole here. So if compass here is a North Pole, that represent the Earth has a South Pole at this position. So walaupun kita tengok peta, kita kata sini adalah kutub utara, tetapi apabila kita anggap bumi sebagai magnet, okay, dia sebenarnya adalah kutub selatan. Kenapa kita tahu dia kutub selatan? Sebab dia tarik kita punya North Pole, kita punya magnet punya North Pole terhadap dia, okay, ke arah dia. So this compass, we have a magnet inside it. North Pole is being attracted here, represent that we have an opposite pole at this position. Okay, it represent that we have opposite pole at this position. So untuk senangkan kita di peta kita panggil dia North Pole. Geographically we call it North Pole. But when it comes to physics, when you treat our Earth as a piece of magnet, this one is actually the South Pole. Alright, jangan keliru ya. Biasanya pelajar dia pening dekat sini. Dia sebenarnya tak payah pening sangat pun. Kalau kamu tengok compass, kenapa dia sentiasa ke arah kutub bila kita arrangekan dia, pusingkan dia sampai dia tunjuk ke North Pole di sini, bermaksud dia sekarang kena tarik oleh satu South Pole. Okay, the reasons why it's pointing towards the North Pole because it's being pulled, okay, it's being attracted by another South Pole. Then this South Pole is actually our Earth. Okay, it's actually our Earth. This is our compass. Okay, the reasons why compass is pointing towards the north, that's because it's being attracted by the South Pole of a magnet. And it happens that the South Pole of the magnet is our Earth North Pole. Itu saja. Okay, itu saja. Alright, so now let us move to the next one. Okay, so we are done with magnetic bar. We are done with Earth magnetic field. Now we are going to move on to our main focus today. Okay, the main focus in chapter 4 is what happens in a current carrying conductor. What does it mean by current carrying conductor? Current carrying conductor in our questions, okay, in our questions dalam soalan, sometimes they call it wire, sometimes they call it coil, or you can also say it is a solenoid. Okay, another example would be solenoid. Any metal bars that carry current, that is a current carrying conductor. So in our case, we're going to focus on this three things. Okay, we're going to focus on what happens in the three things. So how to determine the directions of magnetic field? So directions of magnetic field can be determined by using right-hand grip rules. Okay, right-hand grip rules. So for example, okay, now let's look at the first diagram. Let's look at the first diagram. You have a current going up. Okay, current going up, current is going upwards. So you use your right hand, you let your thumb, because thumb represents the directions of current. You let your thumb pointing upwards, and then you hold the wire, you grip it. Okay, and your fingers, the other four fingers, it represents the directions of magnetic field. So kalau kamu pegang satu wire dengan ibu jari kamu hadap ke atas, itulah arah. Okay, itulah arah kamu punya magnetic field. Okay, your fingers. So cara kamu punya finger curves, dia akan tunjukkan sama ada magnetic field yang sedia ada ini clockwise atau anti-clockwise. Okay, it depends on the other four fingers. Alright, so current going up, then you have a shape like this. If this current is going down, then what happens? If current going down, then you hold it with your thumb pointing downwards, and eventually you obtain a directions like this. Okay, and clockwise direction. Going up, anti-clockwise, and then current going down, clockwise. Alright, kamu sendiri cuba pegang pen Anda. So whenever you have questions like this, usually I encourage students to use a pen. Kamu guna satu pen untuk mewakili Anda punya current carrying conductor. And then Anda pegang pen itu. You hold the pen. You hold the pen with either your fingers, your thumbs going upwards, or your thumbs going downwards. Okay, kamu pegang pen, and then tengok jari Anda, dia pusing ke arah mana. Then that is the right direction. Now, what I want you guys to do, I want you to add one more column. Okay, because when it comes to problem solving, we cannot leave our diagram like this. Okay, what are we going to do? We will sketch diagram from top view. Okay, most of the time top view. Okay, you can sketch from top, from side, and so on lah. Okay, terpulang pada view mana yang akan bagi anda 2D diagram. That will give you a 2D, a nice looking 2D view. So for example, now you have a current going up. You are watching it. You are watching it from the top. Okay, you are watching the current carrying conductor from the top view. Okay, you put your eyes here and then you try to imagine what happened. So if you look at the current carrying conductor from the top view, what you are seeing is the current coming out from the table. Okay, so try to put a pen on top of the table and then you try to look down at the pen. Okay, you try to look down at the pen. So that current is now moving towards you, that is out of the page. So we put a dot here to represent current is out of the page. Okay, current is out of the page. And then if you look at the top view, okay, if you observe it from the top, then you will have a magnetic field in a anti-clockwise direction. So you just draw it. Okay, you just draw a circle around it. Okay, you just draw a circle around it, and then you put the direction. That's it. Okay, that's it. That is how you sketch the diagram. So you need a 2D diagram. Okay, you need a 2D diagram in order to answer the questions. Yes, Kevin, kenapa? Kali kedua dah Anda angkat tangan. Kevin Tran? No? Right. So let us continue. Okay, let us continue. So that is if you have a straight wire. Okay, the first example is a straight wire. The second example is a coil. Now you're holding a coil. Not necessarily a circular coil though. Okay, it could be let's say it could be a rectangular coil. Okay, it could be any other shape. It could be a triangular coil. It could be a square coil. All right. But when you have a coil, what is going to happen? Okay, then you have to know. All right, you have to know. So how are we going to sketch the diagram in this case? So this one, okay, this one we want to observe it. Actually, we want to observe it from the front view rather than the top view. Okay, kita kalau tengok dari siap ya. Saya fikir dulu nak tengok dari mana. Current. This is your current. Oh yes, you can observe it from the top view. I think should be fine. But if you observe, oh no, I think we're better if you observe from the front. Okay, so not just top view, but also a front view. Okay, top or front view. So if you look at it from the front, okay, from the front view, now you have a current flowing in this direction. Okay, you have current flowing in this direction. What does it mean? It means now you have a current leaving on the left-hand side and entering the right-hand side. Okay, so just now current is out of the page. Now you have one current out of the page and one current into the page. Because now you observe the coil from the side view, from the front view. Okay, kamu tengok dari depan. So here is out of the page. All right, and then the other side is into the page. Usually I use a circle to circle the cross and circle the dot to make it easier to see. So this is a current on the left-hand side. Okay, this is left, this is right. Okay, so left-hand side, current is a, terbalik, sorry. Current is leaving on the left-hand side. So you have a dot on the left-hand side. And then on the right-hand side, the current is entering the page. So you have a dot like this. Okay, so basically you can just transfer all this line into this diagram. So the North Pole, okay, this is how it looks like. And then you have a circle, the field. Okay, you have the circle. So you draw it in a 2D form. Okay, you draw it in a 2D form to make it easier to solve. All right, to make it easier to solve. So what you can see right here, you can see at the center, all lines, they are all pointing upwards. Okay, so more line, they are pointing upwards. So here it has a higher strength compared to the side. Okay, so center sini strength dia lagi kuat compared to the side. So that is how you draw it. Okay, that is how you draw it. Is question asks you to sketch magnetic field for the situations given, for the objects given. Now, how to determine the directions then? Once again, you just use your right hand grip rule. Okay, you just use your right hand grip rule. You hold the coil with your fingers following the directions of current. And then when you grip it, Okay, when you close your fingers, you grip the coil, you look at the directions of the magnetic field. Okay, when you close your four fingers, okay, inside the coil, your finger is pointing upwards. Okay, kalau kamu pegang dia, dalam coil, dalam bulatan, jari kamu adalah ke dalam. But if you rotate your hand, then you will see that now B is pointing downwards at the outside of the coil. Okay, di luar coil. Dalam coil ke atas, luar coil ke bawah. Okay, kalau kamu tak percaya, kamu pegang satu wire, pusing kamu punya tangan satu round and see what happened. Alright, at the middle is going up. Then if you rotate it until it's going out, then it's pointing downwards. Okay, so it's pointing downwards. So basically, it follows the shape of your fingers. Okay, your four fingers when you hold it, when you grip the coil. So eventually, you will obtain a magnetic field that looks like this. Okay, in the clockwise directions on the right hand side, and then left hand side you have anti-clockwise direction. Okay, dia ikut arah kamu punya jari. Okay, arah jari, 4 jari ini. Okay, these 4 fingers. So it follows the fingers. So if you hold it, you rotate your hand around the coil and see what is the directions of your fingers. That one is the directions of the magnetic field. The last one, okay, the last example, the last application is a solenoid. Okay, solenoid, what is the difference between coil and solenoid? Multiple coil means that now you have a lot of coil, but they are not touching each other. That is multiple coil. When it comes to solenoid, you have just one wire, but then you change the shape. They are being connected like a spring. So that is a solenoid. Okay, multiple coil dengan solenoid, konsep dia berbeza sedikit. Multiple coil, you put a lot of coil, you put them together, tapi dia tak ada tempat yang sambung sekali. But when it comes to solenoid, it looks just like a spring. So that is a difference between multiple coil, okay, multiple coil, and solenoid. So biasanya pelajar dia keliru antara dua ini, alright? Because some of the questions you are given maybe 100 tons of a coil. Some questions they give you 100 ton solenoid. So what is the difference between them? You need to know. Coil and solenoid, they are two different things. When it comes to equations, you have to be extra careful. Make sure you choose the right equation. Because coil, they got their own equations, and solenoid, they got their own equation as well. All right? Okay, now when it comes to solenoid is a bit special, the way you determine the direction. Okay, it's unlike your coil or your current carrying conductor. When it comes to solenoid, thumbs is no longer representing the directions of current, but it representing the directions of north pole. Okay, north pole. So kamu catat ini ya. When it comes to solenoid, thumbs represent north pole, and then the four fingers. Four fingers, it represents the directions of current. So in a coil and in a straight conductor, thumbs represents current and four fingers represents directions of magnetic field. But when it comes to solenoid, it is a bit special. You use four fingers to represent the directions of current and thumbs to identify the directions of north pole. So once you have north pole, for example, in a diagram given, once you know left-hand side is north pole, then right-hand side, it must be south pole. Okay, it must be south pole. How do I know if I have north pole on the left, then right must be south? Because the directions of magnetic field. Magnetic field is leaving north pole. If it is leaving here, leaving on the left-hand side, then where does it come from? It must be coming from the right-hand side. Nah, itu yang cara yang kita tentukan arah. Once you know the directions of north pole, you can then draw the directions of magnetic field line. Okay, north pole, it tells you your field line is leaving on the left. So kalau dia nak keluar dari left, dia mesti datang dari mana? Dia mesti datang dari kiri. Okay, it must be coming from the right. Otherwise, it won't be able to leave the left hand side. And we also mentioned this before, every piece of magnet, it comes with both pole. It must have a both south and north pole. So if you have a north pole on the left hand side, then right hand side must be south pole. All right, right hand side must be south pole. This one, the diagram, It's very complicated. Okay, I'm not going to show you here. I will just give you the picture in the group later on. Okay, because it is very hard to sketch it right now within a limited time. Because you need to draw the circle for every single turn in the solenoid. Kalau kamu ada 10 turn, kamu kena buat 10 bulatan. Alright, so it's quite time consuming. So this one, I will give you the picture later on. Alright, so just right now, we just skip it first. Oh, actually, I think we have an example in a textbook. Here, okay, this is a diagram. This is the top view of a solenoid. Okay, this is a top view. So this is the diagram that you need to put in your table above. Okay, in the previous table. This is a top view. All right. So we are done with the direction. Okay, you need to know how to determine the direction because, like I told you just now, magnetic field is a vector quantity. When it is a vector quantity, then you need to know both its direction and its magnitude. So direction, you determine it by using your right-hand rule. Magnitude, we can determine it by using this set of equations. Okay, so we have 4 equations right here. If you look at the learning outcome 4.2a, sketch resultant magnetic field diagram. So it is exactly like your electric field diagram, the diagram that you use in chapter 1. So we will learn how to sketch it. And then determine directions of B by using right-hand rule. Okay, so we have learned it in the previous subtopic as well. And 4.2c determines the magnitude of magnetic field by using, so this one is the magnitude, this one is the direction. When you combine these two, then obviously B is a vector quantity. Okay, it is a vector quantity. So as you can see in the learning outcome, you have 4 equations for 4 given situations. So first one, you have for long straight wire, B equals to mu naught I over 2 pi r. And then you have B equals to mu naught I over 2r, the center of the circular coil. You are not looking at what happened outside the coil, but you're looking at the center of the coil. And then you have B equals to mu naught n I, which is at the center of solenoid, and half when it is at the end of the solenoid. So as you can see here, that's why I told you, you have to be extra careful when it comes to problem solving. When you try to solve the questions, you need to identify whether you're looking at the straight wire, you're looking at coil, one coil or multiple coil, or you are looking at a case with solenoid. Okay, different object comes with different equations. So if you are able to identify the object, then it shouldn't be an issue for you to solve the questions, frankly speaking. All right. Okay, now magnetic field density. Okay, magnetic field density, that is our magnetic field strength. So it is defined as the magnetic flux per unit area across an area at the right angle to the magnetic field. Mathematically, okay, it is B equals to magnetic flux over A. And this A is perpendicular to the electric field, the cross-sectional area that is perpendicular to the magnetic field. Okay, so kena berhati-hati, all right? Okay, now one thing that I want you to take notes. Okay, one thing is I want you to take notes. This one is known as magnetic flux. Okay, magnetic flux. B, if you look at the name, it's known as magnetic flux density. Okay, magnetic flux density. So both of them, they have the name magnetic flux in it. So be extra careful. Don't use the wrong equation. Okay, don't use the wrong equations. So magnetic flux, okay, ada simbol magnetic flux, and then ada simbol magnetic flux density. Okay, ada simbol, dua simbol berlainan. So you take note first, you write it down. And magnetic flux density at the same time is known as magnetic field, or you can also call it magnetic field strength. Okay, magnetic field intensity juga boleh. Okay, juga boleh. So Anda kena berhati-hati dengan terms-terms dia, alright? So you write it down first before I proceed to the next part. Okay, sebelum saya proceed ke seterusnya. Okay, actually, I want to correct the symbol. Okay, symbol yang diguna dalam buku kita ada sedikit mistake. This one, it should be macam phi, and then A perpendicular. Okay, A perpendicular. Now, cara yang saya tulis tadi dengan ini tak sama tau. You have to be careful with this symbol. It is not the same as this one. Okay, it is not the same as this one. What is the difference between these two? This one, we call it magnetic flux. Okay, magnetic flux. And this one, we call it magnetic flux. Oops. Magnetic flux linkage. What does it mean by magnetic flux linkage? Magnetic flux linkage, this symbol, okay, this symbol, magnetic flux linkage is equals to N phi. More than one turn, the magnetic flux for more than one turn. Okay, if you're looking at magnetic flux, you're looking at the magnetic flux through one coil, okay, through one surface area, one cross-section area. If you're looking at this is actually capital letter phi. Okay, if you're looking at this magnetic flux linkage, then you need to take into considerations the numbers of turn. Okay, the numbers of turn. Alright, so Anda buat catatannya, Anda ada 3 jenis magnetic flux. Magnetic flux density, atau magnetic flux itself, or magnetic flux linkage. Okay, so bagi Anda 1 minit untuk catat. Okay, buat sedikit catatan. I think this equation is not in your books. I want you to write it down as well, so that you don't get confused. Okay, so that you don't get confused. All right, so we are going to go through all this term again in chapter 5. Okay, this part, when it comes to chapter 4, it just gives you the definitions of a magnetic flux density. So it is also known as magnetic induction, magnetic field intensity, or magnetic strength. Okay, like I told you just now, it has a lot of name. Depends on the questions. If the questions ask you to calculate magnetic induction, then you know it's B. If question asks you to calculate magnetic flux density, then you know it's B. If we say magnetic field intensity or magnetic field strength, it also refers to B. Okay, so it is a vector quantity, and the direction is the direction of magnetic field. The unit is Tesla or Weber per meter square. Okay, you have 2 different units, and they are both new to you. I believe you haven't seen all this term before, Tesla or Weber per meter square. Okay, so Tesla, capital letter T, Weber per meter square, WB is Weber. Okay, so 1T equals to 1 WB, -2, M -2. So that is the unit. Okay, let's see. Straight wire. The magnetic field lines pattern around a straight conductor carrying current is shown in the figure below. So magnetic field around a conductor, when you look at the conductor from one end. So the one on the left-hand side is from the top view, and then the one on the right-hand side is from the bottom view. All right, so when it comes to the questions, usually we will choose either one. We don't leave it in this 3D form, okay? Ini tak sesuai. Why? Because you want to show the directions, you want to determine the direction. You want to state the direction in your final answer. So you need a 2D diagram, okay? You need a 2D diagram. All right, now, the magnetic the magnitude of magnetic flux density B at point P, okay, at a distance R from the wire current carrying conductor is given by, for example, now let's say you have a point P at this position. Okay, you have a point P at this position. So the ways to determine, okay, how to determine the magnitude is by using B equals to mu naught I over 2 pi r. Now, if you look at the question, it say a distance. But if you look at the diagram, actually this point P, okay, the distance between point P and the wire is actually the radius of the circle. That's why in the questions, in the equations, we use r. Okay, it represents the distance from the conductor. So even though we know r, it should represent radius, but in this case, we use the term distance to describe it. Okay, distance from the wire current carrying conductor. But if you look at it in a 2D diagram, actually it represents the radius of your magnetic field. So usually when it comes to this type of questions will give you 1 point. It will ask you to determine the magnetic field at 1 point. Then you yourself have to know how to determine the direction at that particular position. Okay, so for example, kalau soalan bagi kamu point P, it asks you to determine the strength at point P. Then at this point, your B is going downwards. Okay, and then when your locations, let's say this is your point Q. At point Q, your B is going up. So you yourself have to know how to determine the directions of all these vectors. Okay, the questions will just tell you, okay, determines magnetic field at certain point or at a distance that is 2 cm from the current carrying conductor and so on. Then you yourself have to know how to determine the direction. Okay, so B equals to mu naught. Mu naught is a constant permeability of free space, 4 pi times 10 to the power of 7. You don't have to memorize the value. It will be given in the list of constant. All right, so you determine the value, you determine the direction. That is the complete answer. Okay, now if you look at these questions, okay, you look at a straight wire. You can either draw a top view or the bottom view, right? You can either imagine you are viewing it from the top or you are viewing it from the bottom. Meaning that there are two possible answers that you can have in your exam. So in that case, it means that you need or you must show the diagram in your answer so that the examiner understands whether you are viewing the wire from the top or you are viewing it from the bottom. Kamu tengok dari atas ke dari bawah, kamu kena beritahu dengan jelas dalam Anda punya solution. Kenapa? Kenapa saya kata Anda kena beritahu dengan jelas? Because if you look at the one on the left and the one on the right, okay, both at position P, okay, but if you're viewing from the top, then at position B, your magnetic field is pointing downwards. But if you're viewing it from the top, at position P, the magnetic field is going up. Okay, at position Q, just now is going up. In this diagram, it is going down. So you yourself need to know, okay, need to tell the examiner whether you're viewing the question from the top or from the bottom. All right, so ini Anda kena take note. So write down the equations, we'll proceed to the next case. Since kita dah habis tengok cara tentu arah, now we can go through this subtopic quickly. Okay, we can go through it quickly. So basically, this subtopic, it just tells you how to calculate it, which equation to be used for which situation. So circular coil, the magnetic field lines pattern around a circular coil is as shown in the figures. The equations that we use is to calculate the center, okay, the magnetic field at the center of the coil. So meaning that it is here. All right, this is the center. So you're calculating the magnetic field at these positions only. So B equals to mu naught capital letter N I over 2R. This R is now representing the radius of the circular coil. Now, capital letter N, it represents the numbers of coil. Okay, capital letter N, it represents the numbers of a circular coil that you have. So you see how many coil that you stack them together. Okay, you stack multiple coils together, tak sama dengan solenoid. Nah, itu yang kamu kena ingat. Okay, kamu stacking coil bersama-sama, mungkin kamu guna 10 coil, kamu stack them together. That one is what we call multiple coil, 10 turns coil. So you have to use this equation. Okay, kalau Anda buat solenoid, then it will have its own equation. Okay, it will have its own equation. So circular coil, you know how to determine the directions already. And then this is the equations that you need to use. Let's proceed to solenoid. All right, so solenoid is an electrical device in which a long wire has been wound around into a succession of closely spaced loop with a geometry of a helix. Okay, so helix shape, that is our solenoid. The magnetic field lines pattern or solenoid is as shown in the figure below. So this is the diagram. Don't worry, I don't think exam will ask you to sketch this diagram. Okay, frankly speaking, I don't think they will ask you to sketch this diagram. But you still have to know how it looks like. All right. So this is a solenoid. And then solenoid, you have two types. One is you determine the magnitude of the magnetic field intensity at the center, at the midpoint, or inside the solenoid. It is given by equation B equals to mu naught N capital letter I divided by the L, length of a solenoid. Okay, so this is your L, length of a solenoid. So you look at the length. So when it comes to solenoid, okay, you focus more on the length. So mu naught Ni over L. Now these equations can be written as B equals to mu naught small letter Ni. Okay, where small letter N, which is the numbers of turn per unit length, nama dia panggil number of turns per unit length. Okay, number of turns per unit length. So this equation, this one I wanted to add it in your book, sendiri tambah di tepi dia, N over L, capital letter N over L, numbers of turn per the length of the solenoid. Right, so this one is missed out in your books. So you yourself, you add a box beside them and then you write it down. And small letter n represent numbers of turns per unit length. You see how many turns you have in 1 meter, okay, or in 1 cm. That is the meanings of numbers of turns per unit length. And then the magnitude of the magnetic field intensity at the end of solenoid, okay, which is here at the ends of solenoid, it is half of the magnitude at the center. So if you know center is equals to B naught, B equals to mu naught Ni over L, then at the center, this one is B equals to 1 over 2 mu naught Ni, or 1 over 2 mu naught Ni over L. Okay, mu naught Ni over L. So this is the equation for you to calculate at the various position. One is at the center, one is at the end of n turns of solenoid. Okay, at the ends of n turns of solenoid. If you have 1 turns, then you just substitute with n. You just substitute n equals to 1. Okay, kamu cuma letak n equals to 1. All right. So we are done. Let's look at the next one, force. Force is another quite an important subtopic in this chapter. So explain and use magnetic force, determine the directions of the force. So first, a stationary electric charge in magnetic field, it would not experience a magnetic force. But if the charge is moving with velocity in a magnetic field, that is what I told you just now, okay, stationary charge come with just electric field. Stationary charge, moving charge, it come with both electric field and magnetic field. But now, if this charge is moving in another magnetic field, then it has magnetic force. So the magnitude of magnetic force can be calculated. Okay, now I want you to write down the equations in 2 ways, okay? Rather than 1 box, I want you to add 1 more box. Kamu tunggu saya catat dulu, kamu baru tengok macam mana Anda nak catat. So in vector form, okay, in vector form, the equation is F with an arrow equals to Q V cross B. This is the equations in vector form, in a cross product. And when you change it into a magnitude form, okay, in magnitude, you want to use it to calculate magnitude. In magnitude, then the equation is F equals to QVB sine theta. Because you have a cross product here, so cross product, it gives you sine theta. Okay, cross product, it gives you sine theta. So that is the equation, okay, in vector form and also in magnitude. You need to know both, okay? Kamu kena tahu kedua-dua. So now let's see. How are we going to determine the directions of the force then? Just now we used right-hand grip rule to determine the directions of the force. So when it comes to, okay, when it comes to a force, we use Fleming hands. Okay, we use Fleming hands. But what I want you guys to do, there's a slight mistake in your books. Actually, you shouldn't use Fleming right hand for negative charge. This is a wrong concept, wrong idea. We don't do that. We use Fleming left hand only. Fleming left hand, we use it for positive charge. If it is a negative charge, then it simply represents force is coming out from the other side. This is the force for positive charge. Okay. If you have a negative charge, then it simply come out from the other side. This is a force for negative charge. Use just one hand. Why? Because if you use both hands, then you will get confused. In chapter 5, you will have a Fleming right hand. And in a actual situation, we use left hand for magnetic force. Okay, but we use right hand not for force, but for magnetic induction. Okay, induction in chapter 5. So this is a chapter 4. This is chapter 5. So pangka ini, okay, you shouldn't use this one in chapter 4. You shouldn't memorize this one. So F equals to QVB sine theta. How to determine the directions? Oh yeah, one more thing, yeah. One thing that you need to take note is the angle. Since you have V cross B, angle is between velocity and magnetic field. Okay, angle is between velocity and magnetic field. So the directions of magnetic force can be determined by using Fleming left-hand rules, where your thumbs represent force, and then your first finger represent magnetic field, and then this velocity. Okay, the middle finger, the third finger, it represents velocity. And the angle between your three fingers, it should be 90 degree. Okay, 90 degree, perpendicular. Okay, perpendicular. So 90 degree, 90 degree. All right. So that is how you determine the direction. But if you remember the things that we learned in chapter 1, actually, I would encourage you to use right hand grip rule again. Sebenarnya saya galakkan Anda guna right hand grip rule. Sebab apa? Sebab apa? Kalau kamu tengok balik benar kita belajar di chapter 1, di Sem 1, chapter 1. Right, Sem 1, chapter 1. We have a right hand grip rules. Okay, right hand grip rule. I think this note is better. Tak ada. Okay, we have right hand grip rule. Okay, we have something called right hand grip rule, where you use this grip rule when you have a cross product. So it can be applied in any cross product. Okay, as long as you know which quantity cross which quantity. So the result is your thumb. So for example, in this given questions here, in this given diagram here, if we use your right hand grip rule, thumbs represent the first one, your result, which is top, and then your forefinger, it follows the directions of your first vector, okay, which is R, and the second vector is the directions that you curl. Kamu pusing ke arah mana? Okay, kamu pusing ke arah mana? That is the directions that you curl to. So when it comes to the case just now, okay, when it comes to this case, kalau kamu guna right hand rule, okay, kalau kamu guna right hand rule, so this is the equations that we have, right? So if you apply right hand rule, force represents the directions of your thumb. Okay, force represents the directions of your thumb. And then, okay, if you look at just now, okay, this first vector right here, you use four fingers, meaning that in this equation, your forefinger is going to point towards the directions of velocity. Okay, because this is the first vector. So this one is your four fingers. Okay, your four fingers. Four fingers in that direction. All right. And then B is the directions where you close your finger. Or to make it easier, B is the directions of the palm. Okay, B is the directions of the palm. So if you know how to use your right hand grip rule, you can use it in all situation. Kamu tak payah pergi hafal fingers kamu thumbs mana satu, first finger thumbs mana satu, second fingers thumb mana satu. No, you don't have to memorize it. All you have to know is the sequence in a cross product. As long as you have the product C equals to A cross B, then this A, okay, the directions of A is always the four fingers direction. Okay, four fingers direction. B is the palm, okay, or arah yang kamu punya jari tutup. And then C is the thumb. Okay, C is the thumb. So right now, you might not see the advantages of using the right hand grip rule yet. Right hand grip rule, dia memang stick kepada rules ini saja. Once kamu dah tahu dia punya susunan equation punya susunan, okay, thumb sentiasa mewakili variable di sebelah kiri, four fingers, your first vector, palm, your second vector. Okay. Kalau Anda guna Fleming hands, then you need to memorize. Thumb is for which quantity, for force. First finger is for magnetic field. Second finger is for velocity. You need to memorize everything. Okay. When it comes to a different case, then you need to memorize a new set of fingers again. Tapi kalau Anda tahu macam mana guna right hand grip rule, then dia actually lagi senang. Okay, dia actually lagi senang. So now let us go through this one application first before we proceed to the next question. Bila kita tengok equations kedua, kamu akan ada idea yang lagi jelas macam mana kita nak guna right hand grip rule. Okay, after we go through the second equations, then you have a better idea on how to use right hand grip rule compared to Fleming left hand rule. Okay, so a moving charged particle in a uniform magnetic field. Consider a charged particle moving in a uniform magnetic field with its velocity perpendicular to the magnetic field. As the particle enters the region, it will experience magnetic force right away, okay? And it is perpendicular to the velocity. Hence, the directions of the velocity changes, but the force remains perpendicular to the velocity. Now, the conditions to have this one is that the particles, it must enter the regions perpendicular to the magnetic field. Okay, dia mesti masuk dengan syarat velocity perpendicular to the magnetic field. And the moment it enters the field, what is going to happen? It will be pulled downwards by the force. Okay? And it won't just stop. Bila dia ditarik, okay, it will change the directions a bit. When it changes the directions a bit, then the force also sengit a bit. And eventually, you will get a circular path. Okay? Eventually, you will obtain a circular path. So the magnetic force makes the path of the particles is a circular as shown in the figure if the velocity is perpendicular to the magnetic field. Okay, because if V is perpendicular to B, F will always pointing toward the center, okay, at this position. So eventually you will obtain a circle. Okay, eventually you will obtain a circle. So it doesn't matter what charge or what type of magnetic field you are looking at, all of them, as long as they fulfill this condition, V perpendicular to B, then they will give you a circular path. It is very important in calculations. Why? Because since the path is a circle, then we can use centripetal force in this motion. Remember, centripetal force, FC equals to MAC. Okay, kita tulis di luar dulu lah. FC equals to MAC. And in this case, the things that causes my object to rotate in a circle is a magnetic force. Okay, therefore, at the same time, FC is equals to FB. And this is the things that we want to put it here. So FB equals to FC. Okay, FB equals to FC. So FB is equals to QVB sine theta, FC equals to MAC, and MAC equals to MV squared over R. So once again, we go back to SEM 1 punya knowledge sudah. In SEM 1, we learned that FC equals to MAC equals to MV squared over R. And now we try to identify what is the force that causes my object to move in a circular motion. All right. So remember, masih ingat, FC is not any specific name. It just represents the net force that causes the object to move in the circular motion. FC punya maksud, kamu jangan lupa. FC dia bukan mewakili force apa-apa. FC dia cuma nama untuk net force. Okay, nama untuk net force yang menyebabkan objek Anda bergerak dalam bentuk circle. That is FC. So in this case, the force that causes my object to move in the circular motion is FB. Okay, therefore, when you substitute into the equations, eventually you will obtain QVB sine theta equals to mv squared over r. If you rearrange the equations, then you'll be able to determine the directions of the circular path. All right, so r equals to mv over bq. So the period of the circular motion mixed by the circle is given by v equals to r omega. For one complete cycle is 2 pi. 2 pi takes time period capital letter T. Okay, this is one cycle. This is the time taken. Period is the time taken to complete one cycle. Okay, 2 pi equals to one cycle. Time taken to complete one cycle is capital letter T. So from here, we then obtain equations for period T is equals to 2 pi r over v. And the frequency f is equals to 1 over t, therefore it is equals to v over 2 pi r. So all this basically you're just recalling the knowledge that you learned in chapter 6 sem 1. Okay, chapter 6 sem 1 ini benda semua yang kita sudah belajar. So you're just recalling it and then rewrite it right here. All right, so let us move on to the next one. Force on the current carrying conductor in a uniform magnetic field. Okay, so the crucial point in this subtopic is a current carrying conductor. You are looking at just one current carrying conductor. Okay, kenapa saya tekankan one? Because in the following subtopic, you are going to see what happens when you have more than one current carrying conductor. All right, so for one current carrying conductor, okay, I want you to change the equations a little bit. Length, we don't use capital letter L, we use F equals to IL, small letter L cross B. So by just looking at these equations, immediately you know how to determine the directions already. If you use right-hand grip rule. Why? Because like I told you just now, C equals to A cross B. C is your thumb. Okay, C is your thumb. A is your 4 fingers, and then B is your palm. If you compare these two equations, straight away you know the thumb represents the force, and then 4 finger is the directions of the length. Now, directions of the length actually is the directions of current, and then the directions of the magnetic field is represented by the palm. If you use Fleming hand rule as shown in the figure, then you need to memorize a new set of equations, a new set of hand, where your fingers, your thumb represents force. First finger is the magnetic field, second finger is the current. Nah, kamu kena hafal semula. Tetapi kalau Anda memang tahu guna right hand grip rule, yang guna tangan kanan punya, right hand grip rule, yang kita dah belajar di sem 1, basically you just have to know this concept. Okay, and it can be applied in any situation, provided you know the sequence. Kalau kamu dapat sequence dia correct. Okay, if you get the right sequence. So in terms of this one, okay, I also want you to write down in a 2 form, okay? Macam tadi, you buat satu in vector form, equations in vector form is as in given. So F equals to IL cross B. This is the first one. Okay, actually it should have a bracket right here. I bracket L cross B. And then in magnitude form. Okay, to calculate magnitude. To calculate magnitude, F equals to ILB because you have a cross product. So once again, it is sine theta. So theta, okay, theta is always the angle between the cross product, in which it means now you have L cross B. So it is the angle between L and B. Okay, angles between L and B. That is the things that you need to take notes. Alright. So kalau Anda tahu kaedah right hand grip rule, memang senang. Kalau Anda tak tahu, pergilah hafal. Okay, hafal saja your Fleming left hand. Okay, your Fleming left hand rules. So both are accepted in exam. Don't worry. Okay, kedua-dua kaedah semua diterima dalam exam. Yang penting final answer punya arah betul. Okay, yang penting final answer punya arah betul. Alright, now the magnetic force of the conductor has its maximum value and also the minimum value. Why? Because we have equations with angle. Bila kita ada equations with angle, we can always play with the maximum value and minimum value. Okay, so F equals to ILB sine theta. Now you have sine theta. Sine theta, you can have maximum and minimum depending on the angle. So if the value is maximum, when the conductor and the magnetic field, they are perpendicular to each other, meaning that angle is 90 degree. So if angle is 90 degree, it gives you maximum value. If the angle is equal to 0 degree, then it gives you minimum value, as shown in the diagram. So what does it mean by maximum and minimum? You look at the length, okay, your conductor, or the directions of current also can. Because directions of current, we use it to represent the directions of the length. So I and B, if they are perpendicular to each other, you have a maximum force. If they are parallel, they are moving towards same direction, then the force acting on it is 0. Okay, it's 0. So questions, especially objective questions, especially your UPS question, that is the type of questions that they will ask. Which diagram give you the maximum value? Which diagram give you the minimum value? Then in between these two diagrams, maybe they give you different angle, but you don't have to look at all those, because what you want is either 0 degree or 90 degree. All right. So done. Okay, we are done. We are done doing calculating the magnitude and also the direction. So this one, okay, this one force between two current carrying conductor. Previous subtopic, you look at one current carrying conductor. This subtopic, you look at two current carrying conductor. You look at what happened. Okay, you look at what happens in a both current carrying conductor. So explain the magnetic force per unit length of two current carrying conductor. Derive and use magnetic force per unit length. Okay, this equation. So consider two identical wire. Okay, straight conductor X and Y carrying currents I1 and I2 in the same directions with the length L, and they are placed parallel to each other. Okay, so now you have a length. Okay, length should be small letter L. Okay, small letter L. So now they are being placed parallel to each other, and this is your conductor X. This is your conductor Y. Semua ini kamu catat ya, sebab dia kena left out. It's being left out from your books. So you make a correction. Okay, kamu buat correction sini. L huruf kecil, X ini, Y ini, X ini, Y ini. Okay, you have X and you have Y. So you need to label the diagram. So this one is I1. I1 pun tercicil, ada I2 sahaja. Alright, kamu buat sedikit pembetulan. Okay, buat sedikit pembetulan dalam gambar yang diberi ini. So ada beberapa correction di muka surat ini. So pay attention ya. When we go through it, I will tell you where is the mistake. Okay, I will tell you where is the mistake. Alright, so the conductors are in vacuum and their separation is D. Okay, their separation is D. So you put them, the distance between them is D. So in that case diagram, you need to make a bit of correction again. This one should be D. The separation between them is D. Alright, betulkan gambar raja. Betulkan gambar raja supaya Anda tak keliru apabila Anda baca dia punya derivation. So the magnitude of the magnetic flux density B1 on conductor Y due to the current in conductor X is given by B1 equals to mu naught I1 over 2 pi D, and it is into the page. Now, what does it mean? When we look at magnetic field, you cannot look at magnetic field that is being created, that is being generated by yourself. So if you want to calculate the magnetic field acting on conductor Y, you need to look at the neighboring conductor. Kena tengok jiran dia. Sebab apa? Kita tak boleh kira B yang dihasilkan oleh sendiri. If Anda kira B, if you calculate B produced by itself, then D is equal to 0. This will become invalid equation. So what you're going to see, you want to look at the magnetic field generated by the neighbors and is hitting on the conductor itself. So in our diagram right here, conductor X generate B1 and B1 is hitting my conductor Y. And this is the B that we want to calculate. And at this point, kalau kamu tengok arah dia rotate, the B is into the page. Okay, into the page. That is the meanings of B1 is equals to mu naught I1 over 2 pi d into the page. You want to calculate the magnetic field hitting conductor Y, then you need to look at the magnetic field generated by conductor X. Okay? So a conductor Y carries a current I2 and in a magnetic field B1. So what happens right now? This conductor X is generating a lot of magnetic field, right? Conductor X ini dia menghasilkan magnetic field. Conductor Y ada current. When there's a current flowing inside the conductor, means that there is a moving charge inside the conductor. So the situations that we have here, we have right now, is now we have a moving charge particles inside magnetic field, which then will give us magnetic force. That is the meaning of this statement. Conductor Y carries a current I2 inside magnetic field B1. Current means that you have electron flow. Moving electron in a magnetic field give you magnetic force. Okay, it gives you a magnetic force. And the directions of the magnetic force can be determined by using Fleming left-hand rule, or you can determine it by using right-hand grip rule again. All right. So the magnitude of the force is given by, since F equals to BIL sine theta, okay, but remember, F acting on conductor Y, okay, atau kita kata kalau nak senang kita kata F2. F2 yang dihasilkan oleh conductor Y, it is because of the field coming from X, that's why you have B1 right here, okay, but all the other quantity, you use the quantity for conductor Y, except for B, okay. So B1, I1, okay, equations ini, I want you to rewrite it. It should be B1, I1, I2. I2, L2 sine 90 degree, okay? B1, I2, L2 sine 90 degree. So sini kamu semua tukar menjadi L2, tukar menjadi L2, alright? So that is the equation, that is the equations. So when it comes to conductor X, kalau kamu nak kira conductor X punya force, then, okay, let's say this is your F1. So F1, it is equals to B2 pula. Kamu tengok magnetic field yang dihasilkan oleh conductor Y pula. Okay, conductor Y punya magnetic field yang akan kena pada conductor X. Dan itu yang menyebabkan ada magnetic force. Okay, so F1 is equals to B2, which is the force generated by conductor X, is equals to the magnetic field generated by conductor Y, times with the current inside conductor X, and the length of conductor X, sine 90 degree. Alright, so sini buat pembetulan, kita tak guna capital letter L. Kita semua stick kepada small letter L. Okay, kita stick kepada small letter L. So in this case, we will have these two equations. And then you need to determine the direction of the force from both conductor. Okay, from both conductor. For a given example, when both current are going upwards, then the force generated by conductor Y, okay, the force generated by conductor Y, it will move toward S, and then the force generated by conductor X will move towards Y. Now both of them, they are moving towards each other. What does it mean? It means now these both conductor, they experience an attractive force in between them. So when the current flow in the same direction, two conductors will attract to each other. How do I know they attract to each other? Because when I determining the directions of the force by using right-hand grip rule or Fleming left-hand rule, I found that my conductor Y is moving toward X, my conductor X is moving towards Y. Okay, my conductor X is moving towards Y. So in this sense, okay, in this case, we have attractive force in between them. They are being attracted toward each other. Okay, they are being attracted towards each other. So the attractive force is then given by F equals to mu naught. Kenapa mu naught ni? Okay, mu naught I1, I2, L over 2 pi d. Okay, derived from the previous example. Okay, the equations that you obtained from the previous example. And actually, it is also equals to your modulus F12 equals to the magnitude of your F12 and the magnitude of your F21. So even though the directions, they are opposite to each other, but when it comes to magnitude, they are all equals to mu naught I1, I2, L over 2 pi d. Okay, mu naught I1, I2, L over 2 pi d. That is the equation. Okay, that is the equation. So from the above equation, if you rearrange the equations, so basically you can just rewrite it as F over L equals to mu naught I1, I2 over 2 pi d. Okay, kamu cuma rearrange daripada equation sebelum ini. So yang penting punya, kamu kena tahu tentukan arah. Okay, arah kita susah sikit nak explain dalam kuliah sebab masa terhad. Nanti masuk tutorial, pensyarah tutorial anda dia akan focus more on how to apply Fleming left-hand rule or right-hand grip rule when it comes to questions. Okay, in the questions. Nanti kamu akan practice dalam tutorial. So don't worry about that. So if the directions, they are upside down, then what does it mean? It means they will have a repulsive force in between them. Okay, they will have a repulsive force in between them. So in that case, F is also equals to mu naught I1, I2, L over 2 pi d. Equation sama, just at the direction. Okay, they're still having the same magnitude, but now the direction is a repulsive force direction. Depends on questions ask you to determine the force acting on X or the force acting on Y. Okay, acting on X atau acting on Y. So itu sahaja. Okay, itu sahaja. So kita cuma ada extra sikit sahaja, I rasa. Oh, we still have 2 subtopic. Okay, we still have 2 subtopic. Now, in that case, I will leave it for next week. Okay, I'll keep it for next week. I'm not going to finish it today. I can't finish it today. So, yeah, I hope that if you have time, of course, you can go through it already. Okay, if you have time, you can go. If you have time, you can go through it already. If no, then just keep it until next week lah. All right, we have 4 more pages. But I will give you the equation first. Okay, I will give you the equation first. So equations, okay, equation for this one is, again, we have a 2 form. This is in magnitude form. You're given the one in magnitude form. In magnitude, and then in vector. Okay, in vector form, you have tau equals to Ni A cross B. Nampak tak? Ada lagi C equals to A cross B punya format. Bila kamu ada equations ini, it means that you can determine the directions of torque by using right-hand grip rule again. Kalau kamu ada soalan begini, kamu akan dapat tentukan arah dia guna right-hand grip rule lagi. Okay, so this 2 subtopic is just a very small subtopic. Okay, if you have time, you go through it first. If no, okay, we'll discuss it next week. I think one more, here. One more equations right here. This is V equals to E over B. Okay, V equals to E over B. So you write it down first. So if you got the questions already, the assignment questions, then you can try it first. Okay, if no, then you can try it after we are done discussing these 2 subtopics next week.